Hello, in this video we continue the sampling demonstration. So we have here the means of samples of size 5 from this parent population, and here we have means of sample size 25 from the same parent population. And we can see that the spread of the possible sample means gets smaller and smaller the bigger the sample size gets. So by the time you get to a sample of 25, it's incredibly unlikely you get something even as far as this away from the real population mean. And we can justify that, which we didn't quite get to in the last video, by saying that when you're taking an individual value, it's quite possible that you could get something up here. It's not that unlikely. But if you are going to get a mean of, say, 25 up here, that would mean that when you take the sample, you have to get so many big ones and so few small ones. It just becomes incredibly unlikely. You can take a sample of 25 and find that the mean is up here somewhere. So that's why it all becomes much more concentrated down here. So a big advantage of taking a sample, and especially as big a sample as possible, is that you can be pretty confident that your sample mean is going to be one of these, and it's going to be pretty close to the true population mean. So that's a great advantage of taking a sample. Now, one downside to this is that it relies on this assumption that the underlying values of the individuals, so the individual people or trees or fields or fish or whatever it is, they follow this neat normal distribution. Whereas, as I said in the lecture, and you might know that many things don't have this kind of distribution. So really in the real world, if we get rid of that, in the real world we might find that many things we're interested in have this kind of distribution, skewed. For example, land. Some people have got no land, quite a lot of people have got a tiny patch of land, and just a very few people have got a vast amounts of land because it's so unequally distributed. So this skewed distribution, well, how does that affect when we start taking samples? So take a sample of size, well, let's go straight to 10,000 samples, or let's keep the video short, 10,000. So what we can see here is that when you have sample size 5, well, here's the population mean up here, and here's the mean of the samples of size 25. So it's the mean of the sample means is still pretty close, and it's very close again with the 25. But the most important thing is that here it's very skewed, but here that skewness is only just visible, and here it's pretty much gone, and you only have a sample of size 25. And what we find is that even for a skewed sample, even for a skewed population, when you start taking a sample, that skewness disappears, especially when you get larger sample sizes. Now, if you start presenting this to some people that really don't like quant methods, I say, well, look at this, you're still assuming that here there's a really smooth distribution. Of course, the real world's not like that. The real world is much more like this. It's kind of a complete mess. You've got all this kind of horrible stuff like this going on. I mean, more people there, there's a bit of a bolt with nothing there, and holes in it here, and maybe a bit more there. Now, what if you have a really messy thing like this, and then start taking samples? Now, that's going to really muck up your theory as well. Let's take 100,000 and see what we get. 100,000 samples, you see that, yeah, you can still see a bit of a mess there, but even by the time you get to size distribution of means with n is 25, pretty much you're back to a normal distribution again. So you have a second amazing property of sampling, which is that not only the first thing, not only does the spread of the sample means get smaller and smaller the bigger the sample gets, but whatever the underlying population, even if it has no kind of regular distribution at all, whatever the messy thing is, as long as you take a random sample from here, the bigger the sample size, the closer this gets to just being a perfectly symmetrical normal distribution. And those are the two reasons why we use sampling and why we like to have a big sample. One, so that the spread or the standard deviation of the sample means gets smaller and smaller, so we know we're not going to get too far away from the mean. That's the first one. The second one is that it does no longer matter what the underlying population is. Even if it's completely non-normal and irregular, we can still treat the sample mean as though it comes from a normal distribution, and therefore all the formulas and methods work fairly accurately. Okay, thanks for watching.